Hello. Thank you for taking the time to watch this presentation on Let's Just Stop Writing Requirements. We can't write them properly anyhow. I think you need some prior knowledge of system, software engineering and project management in order to get the full benefit of what I'm going to talk about. There are also some hidden note slides in the handout. There are times when I will gloss over something and then you will notice that there's a missing number in the presentation, and that means there's more explanation in the handout and the occasional reference to prior YouTube videos that contain more information about the topic. So what I'm going to talk about today are the perennial problems of poor requirements exist despite numerous efforts to tackle the problem in systems, software engineering and IT projects, and also as it affects project management. I'm going to talk a little bit about the complex and complicated requirements generation process and its reliability. And then I'm going to apply systems thinking to introduce an innovative solution, which I call object-oriented systems engineering. And I'm going to explain a little bit about how it might work. The attributes of a requirement have been known for a long time. They're feasible, atomic, complete, traceable, sufficient, verifiable, not necessarily testable. For example, how do you test a fuse? You plug it in, you blow it, that was a good fuse, now we'll install it in the equipment, right? Don't think so. Adequate, consistent, understandable, unambiguous, and manageable. Facts in a vacuum. We've known about this for 40 years, and so many poorly written requirements are still being produced. Something isn't right. So look at it from the big picture. This is applying systems thinking, and you will notice that there was a hidden slide right at the beginning. The perennial problem of poor requirements still exists. Ivy Hooks presented Writing Good Requirements at the CESE International Symposium in 1993, and there probably were people who wrote about it before then. There's the International Requirements Engineering Board, and they offer certification in writing good requirements. There's the CESE Requirements Working Group, which is busy beavering away rediscovering the 20th century world of requirements. There are lots of standards, books, classes, trainers and workshops teaching people how to write good requirements. And CESE's model-based systems engineering is building complex and complicated models to produce a better set of poorly worded requirements. And there are various requirements management tools that can't tell us if a requirement is poorly written. Why not? I produced a tool 20 years ago that could do that. If you look at the standards, each of these standards has guidelines for writing good requirements, and in the military world they're applicable, and yet the military world still produces lots and lots of poor requirements. I stopped collecting standards and documents on writing good requirements in 2003 when I stopped doing some of this research, and I'm sure there have been more books and documents and standards produced ever since. Lessons learned in dealing with requirements include the requirements process has built-in failure elements. What do I mean by that? People can't always communicate their needs. People don't always know the cost of meeting a stated need. People state requirements in their language, and analysts, customers, users, developers, and other stakeholders don't always speak the same language. Requirements from different sources may conflict, especially over time when changes happen. Organizational political issues drive programmatic and system requirements, and they're often hidden. Stated requirements may not be real. There may be hidden agendas, if you look on the dark side, or maybe they're just not thought through enough at the time. And requirements change over time. Priorities change over time. And there's a difference between what the stakeholders ask for and what they really need. And that's why outstanding systems engineers deliver what the customer needs and then the customer is delighted, as opposed to good systems engineers who deliver what the customer asks for. I picked up this cartoon in 1983. The king says to the wizard, "Can you stop the rain?" The wizard goes, "Rain, rain, go away, Alakazot!" And the king complains, "It's snowing." So the wizard asks, "What is it you really want?" If the wizard had had some acceptance criteria or a model of the solution situation, this situation would never have appeared, because the wizard would have given the king what he needed, and what he needed would have been pretty much what he asked for. 1983, and it's still happening today. We ignore situations in which something cannot be specified by requirements, and we use alternatives. For example, have you ever had a kitchen designed? You didn't write requirements for that kitchen. You looked at a model on a computer screen, and you moved things around. You took some objects, you moved them around, then you were satisfied with your kitchen. How about the taste? Can you write a requirement for a taste? How about a taste of the last glass of wine you drank? In words, without referring to the label or the vineyard. So after all these years, the perennial problem of poor requirements is still with us. Nothing has changed in 40 plus years, other than the tools have become more subjectively complicated. You have to go on a week's training course to learn how to use a tool. There is something wrong. Now, the definition of insanity is repeating the same mistakes over and over again and expecting different results. This has been attributed to Albert Einstein, but the first citation in the literature is from a pamphlet issued by Narcotics Anonymous in 1981, and it was available on the website last time I looked at it. You may not have realized that there are two requirements paradigms. You may also not have noticed the number jump. Slide 10 is missing. It's a hidden slide, and it explains a little more about this. The A paradigm was the original system development paradigm. It started off by developing a CONOPS, or a model of the situation. The system architecture was then derived, and a matched set of requirement specifications for the system and the subsystems were produced, and then the rest of the system development process took place. That, however, devolved, and the first model was forgotten. And so we're now living in a paradigm where people go get the requirements, and from that they develop a model from which they create the system architecture, from which they write another set of requirements, and so on. Model-based systems engineering is trying to return to the original A paradigm because it's producing a model before it creates the requirements. And it's shown as a linear model for education purposes. So let's take a look at that process for producing requirements. You start with a problem or a need. In the B paradigm, you perform some kind of activity and you come up with a set of stakeholder needs or requirements. You do another activity and you produce a CONOPS, or model. You do another activity and you produce system requirements. You do another activity and you produce subsystem requirements. And another activity and you produce software, network, and hardware requirements. Or what's the reliability of your communication path? It's the reliability of each element as shown in the equation. So how would you improve reliability? Strengthen the reliability of the elements in the path? Yep, we've tried that, but education and training is not having much effect. How about model-based systems engineering? True, it's helping to visualize the needed solution, but it doesn't contribute to producing well-written requirements. Those tools can't tell you whether your requirements are well-written or not. How about shortening the path without losing information? Well, we tried that with concurrent engineering. What's a better way? Well, I suggest a better way is to use a different path to carry the information. It must be designed to have higher reliability and fewer opportunities for errors in communication. Let's go back and look at the essence of systems engineering. Professor Derek Hitchens wrote, The essence of systems engineering is in choosing the right parts, bringing them together in the right way, causing them to interact in the right way, and orchestrating those interactions. A unified whole that performs with optimal effectiveness in its operation environment, so solving the problem that prompted its creation. I had a word with Professor Derek about the use of his word solving and suggested changing it to remedying, and he agreed, because problems are not only solved, they can be resolved, dissolved, or absolved, according to Rosakov. And the remedy can be any one or a combination of any of Akov's 4 ways. So what I'm proposing to do about the perennial problem of poor requirements is I'm going to dissolve the problem. I'm going to change the paradigm so the problem goes away. I'm going to introduce object-oriented systems engineering and project management. This is going to bring model-based systems engineering truly into the 21st century and systems engineering back into the A paradigm. By the way, welcome to part 2 of this talk that I gave 20 years ago. So let's take a look at replacing requirements. Text mode requirements are a communication tool adopted in the Stone Age. Many current problems are more complex and involve multiple stakeholders. Computers are provided tools and techniques that can serve as alternative tools. We have computers that do all sorts of things, wonderful things with graphics and simulations and videos. They can communicate concepts in a much better way than text mode requirements. And I mentioned the kitchen and the taste of a glass of wine as examples. The kitchen we do with concepts. The taste of a glass of wine is still beyond technological capability. So let's use an object-oriented approach to replace text mode requirements with properties. Now I pulled this slide from my class. By the way, there are slides from my various classes and publications mixed in with this presentation, and I've left the original text at the bottom, so anybody who's interested can go to YouTube or go to my website and find it. Requirements are performed by functions which are grouped into functional, conceptual, or logical objects which are allocated to physical objects. Let's redraw that. I draw the traditional design path. Concept of operations contains use cases or situations or scenarios. From that we produce requirements. Requirements are turned into functional objects which are shown in use cases or scenarios, and then we turn those functional objects into physical objects, hardware or software. Let's consider software as a physical object for the moment because it's something that's actually produced. And then we generate a set of requirements for the subsystems and so on. What I'd like to do is cut out the unreliable middleman in many projects. It may not work in all projects, but it works in a lot of projects, and I'm going to show how. A function with numbers is a requirement. A requirement is a function with numbers. So let's look at a communications function with numbers. We can show it something like this. Take the object inspector and look at the properties and the events associated with an object. And then we can add non-functional properties such as priority, MTBF, the reason the function is being done, the verification method, and so on. We'd have different tables or different columns in the table associated with each attribute. Clear, unambiguous, and so on. So we expand that object inspector to include the non-functional attributes like so. Could an expanded version capture the entire performance of the component? Logical, functional, or physical? I think so. Look at the attributes of a requirement, or the attributes now of a component, exactly the same thing. It's much easier to see exactly what is needed when it's written in this way. But we can also use specific and generic properties from the object-oriented world. We have stakeholder wants and needs, and they go into the model, but what else goes into the model are requirements or constraints from various other sources that you can see here: government, lessons learned, similar systems, other sources of information, and so on. And we can consider the stakeholder wants and need as solution specific, and all the other ones as solution generic. Well, generally, when we're building a system, it's an instance of a class of systems that has already been built before. And so now we can inherit properties from that generic class that has been built before. And so by looking through those properties and seeing whether they're applicable to our system or not and how they're modified, it improves the completeness of the properties that need to be in the solution system or final product, and so improves the probability of meeting the needs. Object-oriented systems engineering is MBSE on steroids. Text most requirements free. Models are only part of OOSE because it's using data in an integrated information environment. It integrates product and process information in the IIE, and all personnel and tools access information in the same database, much like MBSE is trying to do in the front end. This stretches it out across the entire system lifecycle. So anybody in the development process who needs that information gets read-only access to it out of the same information base. Nothing is lost in translation along the timeline of the system lifecycle. And it can readily provide smart features not available in the current system software and IT development paradigms, and I'm going to go through some of them and give you some examples. There's a tremendous potential for tool creators and vendors because this is way above what the current MBSE tools are doing. It integrates systems engineering, software engineering, and project management tools, and so there's going to be a demand for interface standards and tools that can use information from all those areas combined. And it follows the extended problem-solving process. I talked about MBSE on steroids. Well, how about steroids? Systems thinking eliminates requirements and objectively increases delight and satisfaction. Let's look at the extended problem-solving process. From a functional perspective, we start with a problem, there's the system development process, and then there's a solution. Nope, that's not right. We don't start with a problem because somebody has to define the problem in the first place. There's an undesirable situation or problematic situation of some kind. We visualize a future. I call it a feasible conceptual future desirable situation. The undesirable situation corresponds to the business process reengineering as is model. The FCFDS corresponds to the 2B model. This gives us a problem. What's the problem? Well, in this case, the problem is how to transition from the undesirable situation to the FCFDS. We go through the system development process, we come up with a solution. We're finished, right? Wrong, because the solution exists in an actual situation at a later time. We then have to check, is the situation still undesirable? If it's not undesirable, we've remedied the original problem, all the work is done. If it's still undesirable, or part of it is still undesirable, then we loop back to an undesirable situation, and if the budget permits and we go back through the loop, or a new budget comes up to fix new problems and so on. What we need to do is show it this way, because we don't actually loop back, we just repeat the process. So the first part is one block of lines on a Gantt chart, and then we repeat the process. There's another block of lines on the Gantt chart that shows the second iteration of the loop also takes time. So when we produce the system physical architecture, traditional systems engineering creates a matched set of requirements with linkage, traceability, and so on. And then we have work breakdown structure and a product breakdown structure that don't necessarily match, and there are problems inherent in the process due to this mismatch. On the other hand, object-oriented systems engineering has a matched set of object properties, not requirements, with the same traceability. And in this case, the product breakdown structure is equal to the work packages. There's no mismatch, and I'll show that. There's no gap between system and software architectures. So object-oriented systems engineering can also be taught using the waterfall educational view or baseline project Gantt chart. And what I'm going to do now is go through the 4 early states in the OOSE system development process. We start with the problem discovery state. Remember, I said it follows the extended problem solving process. Then it goes into the solution conceptualization state, the preliminary architecture state, and the architecture selection state. And I'm going to highlight OOSE aspects of these states, and there are hidden slides which go into more information. So watch the numbers skip. Did you catch that? 28 to 30? The problem discovery state creates an as-is model of the undesirable or problematic situation, and here I'm using the word problem as meaning as undesirable aspect of the situation. That hidden slide we just missed explains the different meanings in the word problem. We identify the symptoms of the undesirability, and we document the properties of the function performed by entities in the model. Checkland soft systems and methodology is a very useful tool in this state. And we terminate at the usual review. In this case, it's a problem understanding review. The solution conceptualization state creates a would like to be functional model of a feasible conceptual future desirable situation, or a CONOPS, or something we developed 20 years ago at the University of South Australia, and we called it a operations concept harbinger. And the customer was really delighted with it. The customer and the developers published a paper in the Australian Systems Engineering Tested Evaluation Conference, or the Regional Systems Engineering Conference in Australia 20 years ago. It contains the undesirable situation without the undesirability. This is where the root causes of the undesirability need to be determined, because we don't want to build them in to the new system, and improvements with additional functionality or what have you. We document the properties of the function performed by the entities in the model. And of course we terminate at a solution concept review. The preliminary architecture state creates more than one candidate physical architecture. Depending on the scope of the project, we might go to 2 or 3, and ideally one of them is an out-of-the-box response. We map the properties of the functional objects to properties of the physical objects, and the physical objects, as I said before, contain hardware and software, and there's no gap between system and software architecture. It's a traditional systems engineering activity, nothing different there. But it doesn't produce a matched set of requirements, it produces a matched set of objects together with their properties. And it terminates at the usual review. I call it a preliminary architecture review. The architecture selection state selects one of those solutions and it becomes a candidate solution. It's the standard decision-making process. We do this in current systems engineering. We select the architecture or design, and then we create the systems engineering management plan or project implementation plan or test and evaluation master plan that will guide the production and verification of the physical objects or subsystems. And it terminates as a selected architecture review. The rest of the system lifecycle is traditional. We go through the subsystem construction, testing, system integration and testing, O&M, and system disposal state. But we manage properties, not requirements. The SDP design, stakeholder needs are converted to functions with properties. We design for more than one iteration depending on the complexity and technology availability. We use the extended problem-solving process with its iterations. It's similar to traditional software build planning. It's better risk management. Each iteration satisfies parts of the need depending on the priority, whether it's budget costs or need by date or political constraints and so on. It allows for changes during the system development process, and if there are no changes and we can satisfy them all in one iteration, then we complete ahead of schedule and everybody's happy. Except perhaps the contractor, who won't get paid as much because a lot less work will be done. Let's look at some of the things we can do with this. If we have a set of properties, we can list the properties that are wanted, we can list the properties that are willing to pay for, and then once the system is built, we can list the verified numbers and so on. I'll give a demonstration of this in a moment. It helps with exceeding expectations, because if we know what the customer wanted, which is more than they're willing to pay for, if we're making a design decision that allows us to give the customer what they want without them needing to pay more, they're going to be happy. And so it'll help with the delight and exceeding expectations. Steroids. So properties are identified in the problem discovery state. The wanted are identified in the CONOPS or model of the FCS in the solution conceptualization state. Willing to pay for is identified by the selection of the candidate in the architecture selection state, because cost is generally a selection criterion rather than a requirement, although it could be both. And the actual or verified is measured after the operational test and evaluation in its operational environment. So here's an example of the properties of a system object. The name of the function, the priority, the narrative of the function performed, could be a video even, could be a picture. It doesn't necessarily have to be words. The products that the function produces, the acceptance criteria for those objects that it produces, the reason the function is being done, inputs to the function, the willingness to the pay for the function. These properties are not added all at one time. They're added over time as we go through the system development process as appropriate. Notice it contains both product and project management information because it's an integrated information environment. And then there's a corresponding work package with the same identification number. This is the work package to create that system object. It contains much of the same information, but it's on the process path rather than on the engineering path, and so we add cost and schedule information to it, and prerequisites in the process path, the resources in the process path, the risks in the process path, whereas the system object has the risks in the engineering path. So it's a more effective process. There's tight coupling and correspondence between product objects and process objects. Each process object produces a product object. So it integrates aspects of project management and engineering. It uses the integrated information environment. It's a single integrated project database for process and product. And it provides read-only access to information to all the in-process stakeholders. Designers, developers, testers, specialists in the utilities, reliability people who need to develop that information, domain specialists, whoever needs information about what's being done has read-only access to the system. It produces textual or visual, which can be graphical and animated, and audio outputs as appropriate so that each stakeholder sees the information in their own language. So it fixes a few other defects in the current paradigm as well. And there's scope for smart, next-generation, integrated project management engineering tools, as I'm going to show right now. So let's take a look at some views of the project data. We insert the information during the planning and performance states of a project or the system development process into that IIE. Well, a work breakdown structure in this paradigm is not an input tool, it's a hierarchical view of work packages. The input tool are the work packages. A Gantt chart is a schedule view of the work packages. A PERT chart is a dependency view of the work packages. Now these we have in the traditional paradigm. EVA is a cost incurred view of the work packages. But what we also have is a capability for a technical progress review of work packages using something I call CRIP charts, and management progress review of work packages in enhanced traffic light charts. And they're all linked together out of the database. And let me show some examples. But before I show the examples, the benefits of OOSE include significantly lower costs and improved probability of success. We've removed a major cause of project failure, namely poorly written requirements. Nobody's being paid to write them. Nobody's being paid to figure out what they mean in the later states of the SDP. So we simplify and shorten the time taken by the SDP. And risk management is an integral part of the process, which is basically good engineering practice and good management practice. It's not a separate activity. And there's a broad scope and new markets for MBSE tool vendors, as I mentioned earlier. It changes the focus of the upfront customer dialogue from what do you want or what do you need, because when we're using inheritance, we can show the customer a generic model of what the solution might be and say to the customer, how do we change this generic thing to provide what you actually need? And the customer will see aspects of it which were not thought about at the beginning, and it will help articulate a more complete set of, no, I'm not going to say requirements, a more complete set of properties needed. And we can use it without consensus on the underlying cause of the problem, because we're not concerned about the underlying cause anymore. We're going into providing a situation without the undesirability. We do need to know what causes it. And I think generally we don't get consensus on the underlying causes because the different stakeholders are seeing different aspects of the system and they don't realize there is probably more than one underlying cause. And that's why we use the extended problem solving process with its iteration so we can satisfy the higher priority stakeholders and remedy their undesirability on the first iteration and then remedy the undesirability for the other stakeholders on the second iteration. So it maps into the extended problem solving process and the 9 systems model that are described in the literature, and in the handout you can click on those links and it will take you to the publication. The promise of OOSE is there's a place for a professional society OOSE working group to take the lead to work with tool vendors to establish a tool interface standards up front, because we'll need future interfaces to creation tools, software compilers, hardware manufacturing tools in the workshop and the factory, and other robots that will allow the products to be produced. And with the exertion of smartness using expert systems and artificial intelligence for both the process and the product in the custom domain, we can have tools that are custom to specific domains. For example, if we're producing aircraft, we can have smartness of aircraft design built into the tool. If we're producing engines for aircraft, then we can have expert systems and artificial intelligence built into the tool to help the designer part that will perform with the right reliability and so on and so forth. Or we can have generic tools that are the engines that use the additions and plugs-ons, but we will need interfaces to these. Let me give you an example of what I mean. A very simple smart tool example. We have a customer who needs a house. the needs are stated in, he wants the house done in 3 time units, the cost is 100, the thermal insulation is 88, the number of occupants, and the wind force resistance. But first we have to know who the customer is. You may have heard the story. So our customer designs he's going to build the house out of straw. Puts straw into the tool and it gives some numbers. Hey, these are nice. Now remember, we've got a whole load of properties here. Wind force resistance is way down in the bottom. And so we look at the schedule. Hey, we can complete that earlier than needed. The cost is way down, so that's wonderful. And the thermal insulation is even better. And it will fit the number of occupants needed. And we look at all the other properties, and wind force resistance is all the way down the bottom, and we might miss it in that table. If we were looking at a book of requirements, we might miss it there as well. But what the tool can do is it can color it in. When the need and the actual are close, we color it in yellow. When the actual is much better than the need, we color it in blue. When they're exactly the same, we color it in green. But when it's a lot worse than we need, we color it in red. And so the tool will tell the little pig that straw will not work. The tool could even suggest what physical object to use based on looking at the need without the little pig actually making the decision. The pig puts the need in, the tool will say, if you build it out of straw, it's cheap, good thermal, but the wolf will huff and puff and blow it away. On the other hand, you could try bricks, you could try poured concrete, you could apply cinder blocks and so on, and it would give you the attributes of each of them so the pig wouldn't get eaten up by the wolf. Another tool I talked about is enhanced traffic light chart. You're familiar with the traffic light chart that gives you the state of the project as red, yellow, and green. Well, I talked about enhancing the traffic light chart over time. Let's take the traffic light chart and show last time it was yellow. This time we expected it to be green, and it actually was green, and we're predicting next time that it's going to be blue. So last time there was something wrong, now everything is fine, we expected that, and we're going to go much better the next time around. So we add the time element to a traditional traffic light chart, and I got the idea from EVA, which looks at how things change over time. And it also enhances management by exception and management by objectives, because we can set the objectives for each time period. And let me show you how it enhances management by exception in a moment. And we show the reason for the color as well in a moment. Problem, budget, and schedule. Here is a chart that I should have developed many years ago when I was managing multiple projects, and I put together a presentation that took 2 hours to go over the 11 projects. I should have produced a chart like this. You can see very quickly which projects need to be looked at and which don't. Project 4 has had budget and schedule problems last time. We expected the same, we got the same, and we expected it to happen in the future. We need to find out why. Project 2, it had problems and there was a budget issue. We expected them to be cleared up, they weren't, and it's being projected to be worse next time. That's something we need to look into as well. Project 5 seems to have a very happy customer. We're exceeding expectations. Project 6 went fine and it's terminated. Project 7 went from being really bad last time. Not only did we achieve the improvement, we went better, so we're now in the green and we're planning to stay in the green. Project 8 has been fixed. It went better and we're planning to go ahead. Project 9, maybe that person isn't doing risk management. Project 10, everything's been fine and now we're expecting a problem. Maybe that project manager took a course in risk management. And what about 11? We're showing problems all the way through, but there's no impact on budget and schedule. So maybe we've got a project manager who's doing risk management here. He's identifying the risks, bringing them to attention, and dealing with them. There's a YouTube video on this, and the link is right there. What about a CRIP chart? This is a tool that I designed to track the implementation of requirements along the system development process. There's a video there, there's a hidden slide, and so I'm not going to go through it in any more detail. So this is how it would work. We'll take a look at a project. It's gone all the way up to PDR. We can see that there are some new requirements coming in to the system at PDR in ranges 1, 5, and 7. So the number of requirements have gone up from 292 to 318, but that's all well and good, and it may be valid, but what we need to do is make sure that the impact of the additional work due to accepting those additional requirements show up on the EVA cost and Gantt schedule charts. Now I talked about this in terms of requirements because that's what the tool was developed for in the first place. Modifying the tool to work with properties is a trivial activity. And again, there's a YouTube video that explains a lot more about CRIP charts. Let's take a look at traditional risk management. Traditional risk matrix is like so, and what we do is we determine the severity and the probability of occurrence, multiply them together, and we deal with the risks that have the highest numbers. But there is a fallacy there because it means that a risk with a severity high, like the one I've just circled, can get ignored. I prefer to use something called a risk profile. All the risks, they're not multiplied together, they're shown separately. And so you can see that this project, for example, has a lot of risks in severity category 4 and an awful lot of risks in risk category 7. First of all, you need to ask yourself, are these risks reasonable in this specific domain? And secondly, if you are comparing candidate physical architectures and one of the selection criteria was risk, a risk profile would be a very useful visualization to help you make that decision. So I'm talking about computer-enhanced systems engineering, if you want to use application language, not MBSE. And the operations concept Harbinger was one of them. The enhanced traffic light charts, the CRIP charts are other ones, and I've got a few others that I haven't talked about. It's an integrated information environment. It's vendor flexible templates for classes of objects, so they're product templates and process templates, but it does require interface standards for the plugins for the various domains and the various knowledges, and it allows smart questions at both architecture reviews. And it's based on comparing properties, and I mentioned the risk profiles, but how about comparing priorities and estimated costs of creating those properties? If you've got a low priority property that we estimate is going to have a high cost to implement, we can ask the customer right there and then, do you want to pay that because it's a low priority? And we do that in the architecture review by taking down the willingness to pay. That is part of the trade-off of working out the willingness to pay. AI in the templates can do a reality check on estimates to stop low bidding and a feasibility check on proposed process and product implementation. I showed you a very simple example in the 3 pigs situation, but it can be done on aircraft, it can be done on trees, on bridges, on all sorts of things. And so AI and ES can overcome some of the loss of tacit knowledge as experts retire. Some of that knowledge could be downloaded from those people and stored in AI or expert systems. And we can use risk profiles to compare designs or architectures. And I first used computer-enhanced systems engineering to differentiate it from computer-assisted software engineering. So we would be using a different acronym. Back in 1995. Wow, time flies. Talking of time flying, in part one of this presentation, I ended it by saying systems engineering is all about ensuring that all the properties of the system as delivered are at least equal to the properties of the system needed. Thus, it is requirements free. Let me take a moment. Have you recognized the defects in the current requirements paradigm? Are you interested in the OOSE paradigm? Find out if you can make the transition from requirements to objects. Join me in a small select group for at least 30 days for free. Full access to 2 of my programs. Log on to therequirement.com, read about the program, and click on the button, and you can have access to everything in the class. If you're interested but don't want to try the programs at this time, well, talk to me and others in the online OASIS Cafe using Zoom Mondays to Thursdays. I'm usually on at Thursday and Monday at those times. If you're watching the webinar live, I'll take questions and comments in a moment. And you're still welcome to join me on Zoom in the future if you come up with some other questions. Thank you for your time.